One of the topics we haven't yet talked about, both in the context of the pendulum problem and in general, is, well, okay, we understand how to find the units of a slope, right? By maybe sketching a graph and just noting that the units of a slope are the units of the vertical divided by the units of the horizontal. So in this example, meters per degree Celsius or centigrade. What we haven't talked about yet is how to get that number. How do we get the number which is a slope? How do you compute a slope given a set of data? That's a numerical task. So let's take a look at that numerical task right away. One of the ways we can help to tell the story of a relationship in science is by presenting a set of data. And in this particular question, we didn't have data to begin with. Instead, we had this equation. But we should be able to go from an equation to a set of data simply by picking some values for our, let's say, our independent variable, and then using the equation to compute the corresponding values for the dependent variable. So let's start by picking the simplest value that we can pick for our independent variable. Let's pick t equals 0. Keeping in mind here, T is a temperature in degrees Celsius. So what value of L is going to correspond to the value T equals 0? How are we going to find that? How do you use an equation to find a value for L that corresponds to this value for T? Just plug it in. Yeah, no, there's not really too much of an art to it. We'll just put in 0 degrees Celsius for T, and then compute and find out what we get for L. So 1.210 times alpha times 0 plus 1.210 meters. Well, luckily for us, since T was 0, this entire factor here goes away. And so what we end up getting is 1.210 meters. Which is why the authors of this problem get away with making the claim that this 1.210 that appears in the equation is the length of the bar, the length of the pendulum, in meters, when the temperature of the ambient temperature, I guess, is 0 degrees Celsius. And that gives us on our graph a single data point. Right? And that single data point would be here where T is equal to 0 and where L is equal to 1.210 meters. So there's the point that corresponds to on our graph. But in order to continue telling the story, we probably need more data points. So let's pick a different temperature. What other temperature do you like besides temperature 0? 25 degrees Celsius, which is about, what is 25 Celsius about? It's about room temperature, yeah. So it's probably about 25 here right now. So then we just need to take that 25 and use that instead of 0. Plug that in. Figure out exactly what this model is going to tell us is the length of this bar when T is equal to 25. So we just need to do a little bit more arithmetic this time. Multiply 1.210 times alpha, and we have a value for alpha. It's just 1.9 times 10 to the minus fifth. Multiply that by 25, add 1.210, and let's see what we get. All right, so when you do that calculation, you find out that the length of the bar at room temperature is actually only a little bit longer, length of the pendulum, 1.210023. I'm sort of temporarily here forgetting about our significant figures, because if we just go to 4 significant figures, we actually can't tell the difference between 1.210 and this number, 1.210023. So just including a few extra decimals just so that we can see that difference a little bit more. So then, of course, I could take that number and add a data point to our graph for that particular observation. So when the temperature is 25, the length of our bar, 1.210023. So I'm going to get a second data point. And it turns out that for a linear equation, 2 points is enough. Having 2 points, according to, and this is geometry, now according to the postulates of Euclidean geometry, also works in hyperbolic geometry, but not in spherical geometry. According to those postulates, between any 2 distinct points, there is one and only one straight line. And here it is, plus or minus. So as soon as we have 2 points, we have all the information that we need to completely determine a linear equation, a linear relationship. And then my question again is, from this information, how do we get a slope? Now we have our data points, so we're telling a numerical story now. We've sketched it out as a graph, so we're telling a graphical story. Where does the slope come from? How do you compute the slope with this information? Where does the slope come from? From those 2 points, what do I have to measure? Right. I've got to measure a difference in y's and a difference in x's and divide. Put one over the other. Now, in place of y's, what are we talking about here? What's playing the role of y's? Right. I'm taking a difference in the lengths, which, again, on this picture, that is a vertical difference. Right? It's the length of that little vertical line segment, or correspondingly, this little vertical line segment back on the L axis. So to get that, I just need to subtract 1.210 from 1.210023. So 1.210023 minus 1.210. And so my numerator is 0.00, oh boy, how far out do I have to go here? 4 zeros and then 2, 3. There we go. So that's the height of this little line segment. And again, because that's a vertical difference, the units of that difference are the same as the units of the vertical variable, namely meters. So that's the numerator of the slope. The denominator, then, just want to do the same thing except with my independent variables, which are here, the temperatures, T2 and T1. And there again, I would be measuring the horizontal difference, or if you like, it's the difference on the horizontal axis between these two observations. And because those temperatures are 25 and 0, that's a fairly simple subtraction to do. We just get 25. And again, the units of that are going to come from the units of the corresponding variable. So that's 25 degrees Celsius in the denominator, and 0.000023 meters in the numerator. And again, now you see where the units of the slope are coming from, because upstairs we have meters and downstairs we have degrees Celsius. And then all we would have to do is divide one by the other. Divide that by 25, and I'm going to get 0.00092. Actually, 0.92. Hope that's right. And so there we get a slope. We get a number which describes the slope of this line. A single number, and inside of that single number is a story of a relationship between two quantities. So that's why slope is a bit of a skull breaker. First time that you are really asked to contemplate what a slope means, where it comes from within a context, is that even though it looks like one number, it is really telling a story about a relationship between two numbers. That's why it's interesting. That's why it's powerful. So let's unpack that story into a sentence so we can be done with this pendulum problem and be able to move on today. First, let's write this number in scientific notation. It's going to be 9.2 times 10 to the minus, what is that? 1, 2, 3, 4, 5, 6. Meters over degrees Celsius. Now, here's my little trick to telling the story of a slope. Every slope is a single number, and yet it is also a relationship between two numbers, in the same way that in mathematics, every whole number is a single number, but it is also a fraction, a ratio. Every rational number is a ratio of one number to another number. So what I want to do is I want to see this one number, my slope, see it as being a fraction. In other words, I'm going to take the units of its numerator, the meters, and I'm going to keep those in the numerator. Then I'm going to take the units of its denominator, put them down here. But in order to keep this number the same, I need to attach a number to the denominator. Well, in order to keep the number the same, I'll give it the number 1 downstairs. So any slope, write it as a fraction, and give the numerator the units that the numerator had, and give the denominator the units that the denominator had. Because this is now going to let me interpret the slope, tell me exactly what this means. So this is a story about change. It's a story about the changes in these two quantities. So I'm going to take the denominator and the numerator, I'm going to write sort of half of a sentence that describes each one, and that will tell the story of the slope. And that story usually starts with the clause for every. So starting from the denominator. For every increase of 1 degree Celsius in temperature, of 1 degree Celsius, then the numerator says that this pendulum, the length, increases by 9.2 times 10 to the minus 6 meters. So the numerator and the denominator are telling a story together, right? Neither one of them should be understood by itself, but rather they both together make this entire picture of a slope. That tells me that whenever the temperature goes up by 1 degree Celsius, the length of my pendulum goes up by 9.2 times 10 to the minus 6. By the way, why am I using the word increase here? How do we know where we should be saying increase for this particular slope? Where does that come from?
Because it's positive slope.
Because the slope is positive, and looking at our fraction, what in our fraction is positive?
9.2 times 10.
That's positive. And so because that's positive, we have an increase of 9.2 times 10 to the minus 6. What about the denominator? Denominator is also positive, and so that's why we say an increase of 1 degree Celsius. So now let me ask you this. What's going to happen to this bar if the temperature decreases by 1 degree Celsius? Same relationship, just what happens if I decrease the temperature instead? I'm with Caitlin on this one. When the temperature decreases, the length also decreases. How come? Because the slope, Mike said it before, the slope is a positive number. And what does it take to make a fraction positive? What do we know about its numerator and denominator if the fraction is positive?
It has to be the same sign.
The same sign, exactly. So having a positive slope means that when the denominator increases, so does the numerator. When the denominator is positive, so is the numerator. And conversely, when the denominator is negative, so is the numerator. So because this had a positive slope, there is a positive correlation between length and temperature. If we had a negative slope, it would be the other way around. That an increase in one quantity would lead to a decrease in the other, if the slope were negative. But here, increases and decreases in these quantities are both in the same direction. So when we jack up the temperature, the length of the pendulum goes up, and conversely, when the temperature goes down, the length of the pendulum also goes down. So now we've told this pendulum story in as many different ways as possible. And it started as an equation. It started with algebra. From there, we sort of started sketching a picture of what this relationship might look like. We then went to some data. Right? We picked some values for our independent variable t, and we figured out what corresponding values of the dependent variable L were at those various numerical values that we chose. And from that data, we computed the slope just by finding the difference between the corresponding measurements. And then once we had those differences, dividing those differences one by the other gave us our slope, and viewing that slope as a fraction allowed us to do this very last task, which was to tell the story. What does that slope mean?